Without taking too much of your time, I would like to invite Ingrid to make her presentation. Ingrid, you're welcome.
Thank you. Let me share my screen. I hope you can see my screen.
Yes, we can see it.
Okay, so good evening. I'm Ingrid Kintu. This evening, I'll take you through a presentation about one of the projects that my team and I was working on. It's entitled Displaced Communities, Environmental Change and Sustainable Livelihoods in Uganda. By design, this project leveraged on the strengths of remote sensing and social sciences research approaches to explore the impacts of population displacement on environmental degradation and the subsequent development of sustainable livelihoods in Uganda's refugee districts. For this particular project, we have the University Landy in Scotland, and the project was funded by the Scottish Funding Council and the Global Challenges Research Fund, GCR. A brief introduction. Uganda is one of 4 top refugee hosting countries in the world and the largest in Africa. And this is as a result of the surrounding geopolitical context and Uganda's progressive refugee laws and policies. Refugees in Uganda are afforded a lot of freedom of movement, the right to work, provision of social services, and are allocated land for residential and agricultural use in the settlement. However, the refugees heavily depend on natural resources to meet their needs for shelter, for food, fuel, and income generation, and this has caused environmental change and degradation in and around the refugee settlement. The increasing demands for fuel, wood, and timber amongst the growing populations in the settlement has put a lot of strain on the forest resources, and this has threatened biodiversity as well as the provision of ecosystem services, which are very critical to both the refugee and the host community's livelihood. And yet these dynamics differ depending on the social culture, the political, economic, and the ecological factors which are specific to local settlement context. The overarching aim of the project was to explore how displacement of people impacts environmental change and the subsequent development of sustainable livelihoods. And the specific objectives were to examine the nature and extent of environmental degradation in different refugee settlements using satellite remote sensing and field-based observation, understand the various ways in which refugees and host communities living in or around new and long-term refugee settlements interact with the environment and the ecosystem services. Also to explore the variety of knowledge and values of refugee households for understanding how the environment is used, and then finally offer recommendations for the management of increasing pressure on land resources within sustainable livelihood practices for development and policy programming. So for this particular presentation, I'll focus on the objectives that the remote sensing cluster looked at, which are the first 2 objectives: examining the nature and extent of environmental change and understanding how the refugees and host communities interact with the environment and the ecosystem services. On this slide, I'll talk a bit about the satellite image data that we use, and the data that we used was obtained from different portions of the electromagnetic spectrum. Whereas these data sets can be used alone, we found that they have greater benefits when they are combined. They become a very powerful source of information. And as the presentation progresses, I'll show you where exactly we had to combine data and where we had to use it individually. So the first data set that I'll talk about is a Sentinel-1 SAR data. It is synthetic aperture radar data. And this data is very good because, of course, we are able to get acquisition. And it's not affected by cloud cover. And it's also very good for biomass studies, such as this one. We use the VH polarized data, and this is because vertical send, horizontal receive polarized data for SAR images is very good for volumetric scattering, of which volumetric scattering is what is a major characteristic of vegetation. So we found that using this particular data gave us the kind of results that we were looking for. And this data has a 10-meter resolution and a 5-year archive. We also used Landsat data. It is mid-resolution data of 30 meters spatial resolution. It has a 40-year archive, and we used data from Landsat 5, 7, and 8 sensors. We also used Sentinel-2 MSI data. And this is still mid-resolution data of 10 meters and has a 5-year archive. And finally, we also used high-resolution data from Planet Labs. It has a spatial resolution of 3 meters. Moving on to the methods, different approaches were adopted for Kyangwali and Bidi Bidi refugee settlements, and this was done to account for the differences in the ecological setting, things like seasonality, phenology, as well as the land cover types. For Kyangwali, separate methods were employed to detect changes in land cover and greenness, where greenness is a proxy for changing productivity and clearance of vegetation within the settlement. So we performed supervised image classification to illustrate the landscape before the recent influx of refugees in Kyangwali in 2016 and more recently. And we obtained two images, and we acquired this data in January during the dry season. This data was downloaded from the European Space Agency's Open Access Hub portal, and this is freely available. This data particularly was obtained in January, which is a dry season, because we have the best chance of obtaining cloud-free data. And also research, a lot of literature says that it tends to have a higher accuracy when compared to those acquired at maximum greenness in the rainy season. So we decided to go with these dates, with this month in the year. The images were atmospherically corrected, using the dark object subtraction, and eventually the classification was performed using the maximum likelihood classifier. The land cover classes and training sites were derived from high spatial resolution, Google Earth imagery, and also transit mapping field activity. We were able to obtain this data. So the data we obtained in the field was used both for training and also for validating the data. Eventually, post-classification change detection was passed. For the change in greenness, these are changes in ecosystem productivity and greenness, and these ones usually manifest as seasonal changes, which are driven by rainfall and temperature patterns. Those are gradual changes, which are driven by interannual climate variability, and abrupt changes, which are caused by disturbance, such as deforestation, urbanization, and land cover change, generally anthropogenic activity. In order to perform analysis on the greenness, which is a proxy form. In order to perform that analysis, we use the breaks for additive seasonal change detection algorithm. And we decided to use this algorithm because it integrates the iterative decomposition of the time series into trend, into season, as well as noise component. And we performed the analysis in SQL. So what happened is we retrieved the normalized difference vegetation index time series, that is a NDVI. And we did this using processed Landsat data, Landsat 5, Landsat 7, and Landsat 8 for the study area over a 20-year period. And this time series was analyzed by setting the historical and the monitoring periods at 5 years, and we were able to show areas of positive change and negative change, where positive change represents vegetation regeneration and the negative change represents loss of vegetation cover. For Bidi Bidi, it has a savanna and scrub landscape, which contrasts a lot with agriculture and forest dominant landscape for Kyangwali. So we found that because of these differences, the methods which were used for Kyangwali were not appropriate for Bidi Bidi. And this is where we used a combination of optical and SAR data in order to detect vegetation change, as well as the changes in land cover. So on one hand, for the SAR-only approach, we used Sentinel-1 SAR data from 2015 and 2021, where we determined that vegetation loss. So for this, all this analysis was performed in Google Earth Engine, and all the data was already pre-processed using the European Space Agency's Sentinel-1 toolbox. So what happened is now we just had to come up with a script and then perform the analysis. For this approach, so like I mentioned, we used veg polarized data, vertical transmit, horizontal receive, and this is because the energy which is received from this kind of data is associated with volumetric scattering, and this is very sensitive to changes in relatively low vegetation biomass rather than greenness, which is usually detected code data. So we obtained a ratio between the images, and then we calculated the ratio between the images, and then we set a threshold. Each threshold was obtained after a lot of trial and error because we wanted to make sure we got a representation of in our maps what was exactly was happening on the ground. The final result was a vegetation change mass, which depicted the areas of vegetation change based on values greater than the standard deviation multiplied by 1. For the land cover change, here we used a random forest classifier, and we used a combination of Sentinel-1 and Landsat data, and the images were pre-processed, the random forest classifier was trained, and then the results were validated by combining analysis of high spatial resolution data from planet labs and also the transit field mapping activities, the data we obtained from the field activities. So I picked out, this is not very exhaustive of what we did, but then I'll just try to show what we did. So this was from the time series, and this is for Kyangwali. So this is a time series that was retrieved for over 20 years. However, concentrating on this particular image, this particular map, which has the time period with the influx took place. Find that around here, there's a lot of change from negative change, and this is because a village had been created and it's called Maratatu village. It is in a very fertile area. It is close to Bugoma forest. I'm just neighboring the settlement is Bugoma Forest. This was very attractive for very many refugees. They went, they settled there, they cleared a lot of land to make way for their farms. They are now also going into the forest to get wood for their activities, for fuel wood. They want to get wood for fuel, to construct their houses, to make charcoal which they can sell. A lot is happening in the settlement. So we found that there was a lot of negative change in this area. Moving on to this particular map, the image classification which was done, we found that there was a lot of decline in the forested land. This is within the settlement. There was also a decline in the shrubland areas, an increase in farming, and an increase in the urban settlement and transportation and bare areas, which is expected anywhere people settle. Then for the breakpoint analysis, we found that this was very important just to give an indication of when exactly in the time series the land cover was changing. So still, this was done using the NDVI time series. So what happens is if you have a pixel, say a cell, and for that particular cell, you have an image over the years from 2000 up to 2022. So when that particular cell, which is 30 by 30, for this particular case, we used Landsat data. If there's a lot of clearing that happens in that cell, then we shall be able to know that it was on this particular day that the clearing happened. And that is what we're trying to do. We just picked out a few points and then we analyze the time series, and definitely all the breakpoints we realized came after 2016, and that was after the recent influx of refugees into this particular settlement, and also after Maratatu village was opened. We thought it was important also to do some fragmentation analysis, and that is the map on the left, and we zoomed into Bugoma Forest Reserve. So this is Maratatu village, and then this is a forest reserve. So you can see that when you compare 2015 and 2021, you realize that a lot of fragmentation has happened in the forest. You realize that the cores have actually reduced, the patches have increased, and there's a lot of perforation within the forest, also at the edge, close to where the settlement is. This can be very dangerous because it means we're losing a lot of trees, we're losing biodiversity. That means we are contributing more to carbon. And as you might already know, the carbon cycle is very important to restore the balance of the earth, especially in these times of climate change. So this can be very dangerous in the event, and if this is not stopped or to do it in a sustainable, we might end this forest completely. Of course, amidst all difficulties that were happening around that time with the forest and the contests that were there against it. On the right, this particular map, we had a very diverse advisory board. We had between what we're getting in the SAR images and also what was on ground. So from our field activities, we're able to realize that while stone quarrying is happening, there's a lot of bricklaying, there's a lot of tree cutting, and we found that these activities are actually happening on ground, and the mask was doing a very good job of detecting this area. For the combined optical and SAR analysis, this is now where we use both the Landsat and the Sentinel-1 data, and we applied the random forest classifier. So we classified the settlement and a 5-kilometer buffer for 2015 and 2021. If you clearly look at that training classifiability, you realize that there's a lot of overlap. It was very, very difficult to separate the different classes. However, we're eventually to do so by incorporating SAR. So when we tried to do the classification alone, using optical data alone, it was not sufficient. It was very complicated, especially when we're trying to separate classes like agriculture, shrubland, and the like. But when we added the SAR data, it became possible to separate these classes, and at the end of the day, get a classification that is a representative of what is on ground. So zeroing in on the settlement exactly, we found that wetland areas had decreased, shrubland areas had also decreased, farmland had increased, urban settlement, transport bare, these areas had increased, and then also Banska had increased. However, for the Banska areas, it changes from year to year, because usually when they are burning, the areas they want to clear land for farming, or they want to make way for pasture for their cattle. So it's not exactly that it has increased per se, or maybe we could just say that people are clearing more land to plant more crops, but that particular class was not built on much. Then on the right, we overlay the SAR mask that we obtained, this particular mask here. We overlaid it on this map. And then there's another map that I did not incorporate here, which was indicating the change detection. And we realized they were very close, where the check mask gave us data of degradation as well as the land cover changes with the post-classification change detection. There was a lot of correlation between the two. And that meant that it helped us to validate our results on top of using the field data that we had collected and we're using for validation as well. So just to give some conclusions, now these are conclusions from remote sensing cluster. Like I said, it was a project like there was a remote sensing side of things, there was a social sciences side of things. So these are now just recommendations from the remote sensing cluster. And we found that the remotely sensed data clearly shows landscape fragmentation and tree cover reduction for both case study sites over the recent period of the intense refugee influx. In Kyangwali, the extent of tree cover in the area for Bugoma forest near the settlement decreased by 7.5 between 2015 and 2021, with increased forest fragmentation and a reduction in the mean size of the remaining patches. Then in Bidi Bidi, the residential and bare ground land cover classes increased, resulting in land cover fragmentation and a 50% reduction in tree cover between 2015 and 2021, which is yet to generate. So for the recommendations, we came together, the remote sensing side and the social sciences side, come up with these recommendations. So these are not only from the remote sensing side of the project, but they were combined. And we had recommendations to do with settlement and land use planning. We had recommendations to do with cross-sectoral collaboration and coordination on environment and livelihoods, environmental livelihood interventions, land and natural resource use rate, community participation in forest and natural resource management, and sustainable resources and landscape restoration. And all these are in the report. The report is online, you can access it, it's freely available. We have the report, we also came up with a policy brief, which policy brief, both the policy brief and the final report were made public at a launch, and most of the recommendations that were made from the project have actually been taken up for policy by OPM and the like, and up to now we are still in conversations on how to incorporate them in different activities, and and discussions are still going on about that. So this brings us to the end of the presentation. Don't know if you have any questions that you'd like me to answer.
Yeah, thank you very much, Ingrid, for that presentation. And what I always tell people that is that not only does remote sensing enable us detect change, but most importantly, it helps us to quantify the change. So it is from that quantified change that we're able to make those deductions. We're able to say settlements have increased by this much, vegetation has reduced by a certain amount. And by doing that, we are able to influence policy, we are able to inform decision making, we are able to make informed decisions based on verifiable data. You talked about Google Earth Engine. I was just wondering if maybe after the questions, you could describe what Google Earth Engine is, how it is used, advantages of using Google Earth Engine, yeah, things like that. Thank you. Please, if there are any questions, this is the opportunity to ask Ingrid before she talks about something else. Well, Ingrid, since there are no questions, so maybe you could just describe what Google Earth Engine is.
Okay, Google Earth Engine is an online platform. It's very simple. You can register, and within a day or two, you have access. So it employs the use of cloud computing resources. We no longer have to download the data onto our computers and process it, but rather you do all the processing online. And it runs using the JavaScript programming language. It's very easy, and it has a lot of resources that can help you to learn how to perform the analysis. So you perform all your analysis on the cloud. You don't need to perform the analysis on your computer locally. And that is how we are able to do time series analysis using over 500 images from like over 20 years. So it's a very good platform to use. It's one of many which have come up today. And I would really encourage you to take some time to learn how to use it.
Yeah, so maybe to elaborate more, yesterday, I think, when we had Jesse demonstrating how to use QGIS, and you saw that you had to go to Glovis or whatever, identify the image, download it, classify it. Then if you needed for another date, you would also access it. So let's say you download an image of 1990, another one of 2000, another one of 2010. The thing with Google Earth Engine, it harnesses the potential of cloud computing. You do not, I think Ingrid, I'm right, you don't even need to download the imagery. You just process it on the Google platform, Google Earth platform. So all you have to do is just say, do the script, do the classification, do the whatever that you want to do, and you're not doing it on your computer. You're doing it on their platform. So Ingrid, maybe you can elaborate, or maybe I've said it all.
I think you've said it all, but yes, you're right. You don't need to download any images. You just perform all your analysis online, and then you can download the final product as a TIFF file. You get to select the kind of the scale that you want to download the data at. But that's it. It just makes the whole processing experience much faster and also easier compared to how it used to. And another good thing about it is you don't need to pre-process that data has already been pre-processed before it is uploaded on the cloud for you to use. So pre-processing time is cut out as long as you're able to come up with a very simple script and access the data. They have all kinds of classifiers, whether you want to use the maximum likelihood classifier, random forest, and supervised classification, SVM, you can name it, they're all there. And of course, you're able to do other things like time series analysis. You're able to do the things that you can do within your GIS environment. You're able to do most of that. You can come up with charts. You can visualize your maps still within the platform if you want, or you can just download the products and create your maps using other GIS environment that you might have. So it's very convenient, it's very easy to use, and the good thing about it is they have a very good platform in case you need help. Also, there are very many resources online for you to use.
So in effect, they are shifting the computation burden from your laptop, and it's going to it's going to the cloud. Nowadays things have improved, but I think Ingrid will tell you that when she was a student, to download a Landsat image, you would have to probably come early and try to download, and imagine doing that, trying to download 50 images. That would be demanding. Now that burden is not on you. Furthermore, if you were to do any classification or any other complex stuff, you would have to have a powerful computer to do the processing and things like that. Now you don't have to do that. You need to know the potential of Google Earth Engine. And when we are talking about time series analysis, you don't even need to do 2000, 2010, 2020. You can even look at all the images in that time, and the computations will go on, and you just get a result. What is important is how you do the interpretation. So yeah, that is what Google Earth Engine is about. And this is a typical example of how it was employed. I think, Ingrid, you said you used how many images? 50, 60?
There are very many. Remember, Landsat has a 16-day revisit time, unless maybe there's cloud cover. So you find you're processing more than 500 images, but you're not doing it locally. You're doing it using the cloud resources.
So you can imagine processing 500 images on your computer. That would be, time consuming. So that is the potential, that is the advantage of cloud computing. Maybe you could tell us other cloud computing platforms.
Yeah, then the other one that I talked about was Simple in the presentation, and it's an open forest tool created by FAO. And it's a very good tool as well. And the good thing with it is you can also do R programming. There's a section for Python programming, and you're able to do the time series analysis. You can do the breakpoint analysis, among others. They keep coming up with new tools which are uploaded. So as long as you know where your study area is, you can come up with a simple script, then you can perform the analysis. But they also have click of a button applications, tools that you can use, which still make the processing, which makes processing very easy. And the other one is Data Earth Africa. It's also a very good platform for you. It has a number of tools from water analysis to do with water bodies, whether it is crop security, land cover classifications, among others. So they are still based on the same thing. Using cloud computing resources, you no longer have to do everything on your computer. Even if you have the weakest computer, you can perform this analysis. You don't have to have the latest, I don't know, i9, i7, I'm not sure what the latest is even. But as long as you have a computer, you can access the internet, then you can access these platforms and do your analysis, download your outputs, create maps, and use them.
Ingrid, can I ambush you? Could you, the presentation you made about Digital Earth, could you give some insight in case there are some people here who might be interested in furthering? Of course, our class ends tomorrow, but there may be one or two people who might say, oh, let me pursue this.
Okay, let me pull up the presentation.
Okay.
Sorry, it's taking long. I'm just looking for the presentation, and I hope you can see my screen.
Yes, we can see.
Okay, so I'll give a very short presentation into Earth Africa. It's another platform which is based on the use of cloud computing resources, and I'll take you through the introduction, some of the data sets and platforms and use cases. So what is Digital Earth Africa? It is a web-based platform which capitalizes on the use of cloud computing resources to provide access to free and open analysis ready satellite data for use by African governments, industry, and decision makers. And not only does it provide access to this data, but it also provides a sandbox for analysis in order to track changes in detail. They're able to perform all kinds of analysis to do with flooding, drought, soil and coastal erosion, agriculture, forest cover, land use, land cover changes, water availability and quality, and changes to human settlements, among others. So the added value of satellite data and products which are available through this platform, firstly, you have free access, and it also gives you access to data which is already freely available. This data is already pre-processed, and it's from 7 missions, 7 satellite missions. So that is Sentinel, Landsat, among others. And you're able to get access to both optical and radar data. And this data is analysis ready. It has already been optimized for research, for analysis, and you don't need to download that data. You do everything online. You only need to download your final products. You're also able to get continental derivative services, which are ready for decision making. There's full visibility into the generation of those services. And also, this data is available through, through interactive or programmatic interfaces in French or English. So we are English speakers, so we'll be using the French component. And you're able to perform complex analysis on specific on specific topics which are supported by a large library of open source tools. I'll show you towards the end of the presentation, there are quite a number of tools that you can use, and the good thing about it is they also offer a free learning and support platform, and you're able to ask your questions, just able to sign up and do the entire course, which is a very short course. And after that course, you should be able to stand on your own feet and perform any analysis that you'd like to perform. So for the data sets, services, and platforms, the data sets, they provide quite a number of data sets. One of them is a geomedian annual image, which is used to deal with cloud cover. So as you already know, if you're dealing with optical data, especially for us, we're in the tropics, there's a lot of cloud cover, and that can make it very difficult for us to perform analysis. There is nothing you can do if there's cloud cover. So using these geomedian annual images, you're able to get an image, say for that particular year, no cloud cover, and you can perform analysis like landscape changes, monitoring crops, among others. Then the median absolute deviation, this one is good for detecting changes in the landscape. There's also the water observations from space. Still, this is to do with water, the location, movement of water within the landscape. There's also food security. There's a cropland extent map for the entire continent. And you identify an area that you want to work on, and then you can perform the analysis. It's really not very complicated. Also, the seasonal fractional cover, which allows you to understand landscape patterns and trends. And of course, all these can help you to inform evidence-based decision making. Then you're also able to access NDVI anomaly data, from which you're able to identify different things that are happening over time. As you already know, NDVI is a very good index that is used for vegetation studies, cropping, among others. So you're able to effectively monitor the seasonal and the long-term changes in cropping patterns, or maybe vegetation areas, maybe in forests, whatever you decide to do, it's all possible with the data sets in digital. In order to access that data, you can either view the data on the Digital Earth Africa map, or you can analyze the data, but that should be done within the sandbox. So the sandbox is where you perform all your analysis, and you just simply sign up and you'll have access to their cloud computing resources, and then you'll be able to perform all your analysis. You can also access the platform through GIS software if you wanted to. There are very many ways of accessing it, whether you're using ArcGIS, whether you're using QGIS, the data. How do you explore the data? You can explore, compare the products and services to the Digital Earth Africa map. This is now online, or you can use the web map service in your favorite GIS software, whether it's ArcGIS, QGIS, among others. And if you want to analyze the data, you do that through the sandbox, and you just have to register. You can learn how to use it from the courses that are provided. And then you use the Python code examples, which are also provided for free. So you can tweak them to what you want the code to do, and then you can perform your analysis quite easily. So to give examples of some of the use cases and also maybe to explain more about the training opportunities. This is one of the cases where Data Earth Africa has been used. Someone was interested in knowing how Earth observation can be used to support cotton farming on a large scale. So you'll find that if these are things that you want to do, like through traditional methods, visiting all these areas, it takes a very long period of time. It is very time consuming. It is very laborious. And then I'm able to do all of this using remote sensing data. And what makes it even better is we're able to do that using cloud computing resources, and you have access to data over a very long period of time. Here's another case, measuring crop health. So here, you just simply have to show where your study area is. If you already have an idea of the kind of crop that you are going to monitor, then you'll be able to retrieve the NDVI over that period of time. So you'll be able to look at things like seasonality, when the crops were doing best, and then you can go back in time, try to understand why exactly they did better in that particular year compared to another year. There's a lot of things that you can do, and of course, this is a very important product for a farmer or decision makers in Ministry of Agriculture and the like. You can also use the data to map water extent. And this was done for Lake Baringo and Lake Sulunga in Tanzania. Now, specifically for Lake Sulunga, it's relied upon by very many people, by very many surrounding settlements for drinking, water, fishing, agriculture, among others. And what happens is the extent of the lake varies a lot. And people tend to settle when the water has decreased, and then eventually when the rain season comes and the water is going to increase, people are going to be affected. So using Data Earth Africa, they were able to ascertain the exact extent of the lake at its maximum, and then that is where the decision makers were able to tell the people on ground not to construct or to farm in the areas where the water might exceed and destroy their property as well as their crops. And this is just one of the applications. And then it also used conservation. For this particular case, homing giraffes. You know that because of climate change and also as a result of very many activities that are happening, usually anthropogenic, we are losing a lot of biodiversity. We are losing a lot of land which was previously under forests, but now it is being used for other things like farming and agriculture, for farming and settlement. So by using the platform, you're able to see where the changes are happening, and then also able to ascertain how the rate at which the changes are happening and you can then come up with solutions on how to maybe revert that, or maybe to come up with sustainable solutions where it can still happen concurrently while we conserve our biodiversity. Then it has also been used to save Zanzibar's mangroves, still fighting the effects of climate change, protecting the island's precious mangrove habitat, and they provide a very good blog on how they did it. It was done by SUZA, that is a university in Zanzibar rather, and they did quite good work. So when I share this presentation, you'll be able to go through and see, read through their blogs and try to see what they did in their study. So for the training opportunities, like I'd said, you do most of the analysis in the sandbox. So in order for you to learn how you can use a sandbox, how you can access the data, how you can come up with the different codes, how you can change the code to do what you want, you just simply have to sign up and use that, maybe using your Gmail, whichever, and then you enroll into a sandbox and also the masterclass. That particular masterclass, it is self-paced, it is free, it's freely available for everyone, and you'll have access to videos, recorded tutorials and manuals. You'll have hands-on exercises, and the good thing about it is you'll also be able to, if you have any questions about the code, if something is not working, you can always reach out to the support team, and at the end of it all, you have a certificate of completion, and that is when you have finished the entire course. So it's a very good certificate to have, and at the end of that day, you have learned so much. And maybe I should add the fact that you don't just learn how to use a sandbox, but at the end of the training, they also give you the opportunity to learn how to do Python programming. You don't exactly need to already know how to use Python before you do that training. But then if you want to be better at it, if you want to learn more, then you can also do that particular course which comes afterwards. Then these are just websites for you to access, get more information about Data Earth Africa. Of course, you can subscribe to their newsletters, And then every Wednesday, every week, they have weekly live learning sessions. So if you want to learn how Digital Earth Africa is being used, or the applications that is being used for in different parts on different projects, different areas on the continent, you can always sign up and you can learn more about it. I think that brings me to the end of the presentation.
Thank you very much, Ingrid. Always a pleasure having you and class. This is a great opportunity. Of course, it's up to you to appropriate it. If you want to learn more, this is an avenue you can explore, and it's amazing what you can do with remote sensing. And in this case, we're now looking at cloud computing platform. I will open the floor for 1 minute if there are any questions, or else I will release Ingrid. Yeah, so Ingrid, they are either convinced or confused. I hope they are convinced. So thank you very much. And class, that brings us to the end of our journey of remote sensing. Tomorrow, we shall have our assessment, and that's when I'll know if you've been attending or just yeah, I'll know if you have been attending. And everything that we have learned up to today is potentially coming in the test. So please, let's meet tomorrow, 5:30, to have our test. I haven't set it, so I can't even tell you what is coming. But Ingrid, thank you very much. And thank you for making time to be here. And we really appreciate it. So, ladies and gentlemen, have a good evening and enjoy the rest of your day. Thank you very much.